Dive into the memory hierarchy of modern GPUs. Unlock blazing performance. GPUs run thousands of threads in parallel, but without the right data in the right place, your kernels stall waiting on memory. First, registers. Each thread gets its own tiny ultra-fast workspace, about 256 bytes per thread, accessed in one cycle. Think of them as thread private variables loaded in one cycle. Super fast, but very limited in size. Next up, shared memory or L1 scratchpad. It's on chip shared by all threads in a block, typically 48 KB per block with access in 4 cycles. Use it for data reuse and inter-thread communication. Much faster than global memory but limited in size. Most GPUs combine shared memory with an L1 cache to speed local loads. L1 cache is about 128 KB per SM with 20-30 cycle latency. Beyond that, a larger L2 cache serves the whole GPU, typically 4 to 6 MB with around 100 cycle latency catching global accesses. Global memory is off-chip DRAM, several GBs in size, but with high latency, 400-800 cycles. Coalesce your reads and writes for full throughput and avoid random accesses. Global memory is large but slow compared to on-chip memory. For read-only data, constant and texture caches are gold. Constant memory is 64 KB, broadcast to all threads in about 1-2 cycles if cached. Texture memory adds spatial locality and filtering. Texture cache is typically 48 to 96 KB with low latency for cached accesses. Finally, host memory sits over PCI Express or NVLink, orders of magnitude slower, with bandwidths of 12 to 100 GB/s and latencies in microseconds. Overlap transfers with compute using streams to hide latency. Always keep hot data on the GPU when possible. Key takeaways: keep hot data in registers and shared memory, coalesce global accesses, leverage constant/texture caches, and hide host transfers. Want hands-on demos? Check out the playlist linked below and level up your GPU code.